Okay, so I wanted to start with just writing what I wrote last time with a little bit more detail. So this is where we stopped yesterday, and it's the sort of the main theorem that I'm presenting here. But there's many things around, and what I said is I'm going to try to show at least the main ingredients of the proof of the theorem, but that's going to be later in the lectures. So what the theorem says is the following. It says that if you take the T-sub height function, so this ht comma x, and I define this 1, 2, 3 rescale height function, so I'm rescaling it in the way that I discussed yesterday, then if I assume the following, so if I assume that the initial, I want to show convergence of this process, so of course I have to assume that the initial condition is going to converge. So I'm assuming that the initial condition converges, and it converges in this space. So I'm going to stop just for a moment. We won't really use this much because I'm not getting into details, but this is the space where convergence is happening. So the convergence happens in the space of upper semi-continuous functions, and we have to impose a certain growth condition. This is not really the most general one that one could use, but it makes life a bit easier. So we assume that we have an upper semi-continuous function, which is bounded above by a linear wedge. And the topology is the local Hausdorff topology. So you just restrict the functions to some finite interval, and you use the Hausdorff topology there. If you don't know what's the Hausdorff topology, don't worry. You can actually think mostly at all times as if, so if you restrict to continuous functions, and this process is going to become continuous very fast. So for every t positive, h is already going to be continuous. You can think of this convergence as happening in the supremum norm on compact sets. It's actually even stronger than that. But because of these strange initial conditions that we can use, we need to do everything in this space. So this is the space. And just to have a picture in mind, this is how an upper semi-continuous function looks like in general. Okay, so it's always above. The limit is if you have a jump, then it's always above. But you can take, so for upper semi-continuous functions, it's natural to consider the case that they can take minus infinity as a value. Okay, so you may be looking at a function which is like this, and it takes the value minus infinity. Okay, and we're going to use that actually. Okay, so that's the space. And again, if I have convergence of the initial condition, then the process, as a process in t and x, taking values in this space, sorry, as a process, if you want, as a process in t, maybe I should write it like this. Something like this. Not being extremely precise now because I wrote as a process in t and x, so let's say in UC. So all I'm saying is that as a process in time, so this is a process that's taking values in UC, and using this topology, UC, we have convergence to some limiting process. And what's this limiting process? This limiting process is this HTX. So this is what I'm calling the KPZ fixed point. And this is where I stop. So this KPZ fixed point turns out to be the unique Markov process with, well, let's say, such that, so if I want to say, if I want to tell you the distribution of the Markov, who is the Markov process, it's enough that I give you a rich enough class of finely dimensional distributions. So I'm going to write the one-dimensional distribution. As I said yesterday, I'm always going to write things for one-dimensional distributions, but the finite dimensional distributions come from these extended kernels. So it looks as follows, and it really won't tell you much. If you want to know what's the probability that at time t and position x, this height function is less than a, then this is going to be given by a Fredholm determinant of I minus a certain kernel or a certain operator. I'm giving it this name. I'm going to tell you who's this later on in L2 of A infinity. So it really looks exactly the same at least in structure, as the formulas I showed you for the Ayyer processes, but I'm changing this operator. And I'm going to talk about this operator today. This hypo here, I will mostly not write hypo just because it's too long, but it refers to hypograph, okay? And we'll see exactly how that comes in. So this is the unique Markov process which has this one-dimensional distribution and finite dimensional distributions given by an associated, say, extended kernel formula. Okay, so you can, if you look at the notes on my web page or in the paper, you'll see there what's the formula. But the formula, the formula for the finite dimensional distributions, it looks exactly the same. Again, it's the same extension as for the Ayyer process. What you do this KTX, and then you have to conjugate by these heat kernels and add something below the diagonal or above the diagonal, and that gives you a matrix of operators, and then you compute the Friedman determinant on this bigger space, and you get the answer. Okay. So of course, I haven't told you who this is. I will tell you today, but ignoring that, does this make sense? Because this is really the main point. So I have a Markov process taking values in this space of upper semi-continuous functions. Think of continuous functions if you want. And it's evolving in time, and the evolution is Markovian. So if I know what the interface looks at time, I have my interface, and maybe it's evolving. It doesn't have to be going up, but for the sake of the picture, maybe this is T1, and then it's here at T2, and if I want to know what happens after T2, after time T2, what the interface is going to look like, I don't need to know anything about what happened before. It's just enough to know what the interface was at time T2. No, so what you get, so really, yeah, that's what I'm saying. I was saying that I'm being a little bit vague. So what you get is convergence in the space of, I guess it's right continuous functions from 0 infinity into UC. That's the statement. That's what, okay. So let me make a couple of comments. Maybe one comment, there is something that's confusing and that some people asked me yesterday, but it is confusing, and I didn't have time to point it out yesterday, so I'm going to do it now. So what's the relation between this and the Ayyer processes? So the Ayyer processes should happen here. So first notice the following thing. The Ayyer processes looked something like this. So when I wrote this Ayyer 2 process, or let's say the Ayyer processes, arose as limits of something like this, h of t, h of t, and then I had to put here some constant, which now I know it's a 2, so it's going to be 2 t yeah, no, I thought somebody was saying something. T to the 2/3 x, and here I will have to add actually t to 2/3, and here I have to put, I have to divide by t to the half. And you can see that if I set here t equals 1, so in h epsilon t x, so let me not write it because it's going to be even more confusing. But if here I set t equals 1, and then I do what am I? Oh, t to the 1/3. Yes, thank you. T to the 1/3. Yes, thank you. And it's 2t, not t to the 2/3. Thank you. Yes. Okay, so if here I put t equals 1, and then I let epsilon be t to the minus 2/3, I guess, yes, then this thing is exactly that. So, right, it looks exactly the same. You can check. So, in particular, this means that at t equals 1, this should give me the Ayyer processes. And it does. It will give me the Ayyer processes if the initial condition is the right one. So if I let the initial condition, the H0 here, be this wedge, then, well, that's going to converge to something. I'm going to say what that is later. It's a wedge that's doing this. So it's a function which is 0 at 0 and minus infinity everywhere else. But that's a nice upper semi-continuous function like this. And then at t equals 1, I do get the Ayyer processes. Okay? Of course, if I do the other one, then this is going to converge to 0, and I'm going to get the Ayyer 1 process. So the Ayyer processes are covered here. Okay? So let's say we mark, so 1, setting t equals 1, and epsilon replaced by t to the minus 2/3. 1 recovers the Ayyer processes at t as h of 1 comma x for the correct initial conditions. That's what I was saying. I'm actually going to show you, and I hope, yeah, I should be able to do it today. So this is, I mean, I get it just because on the one hand, I know that I have convergence to this, and on the other hand, I knew from before what the limit has to be. It has to be the Ayyer 2 and Ayyer 1 process. And then a natural question is, well, I haven't yet told you what this is. I'm going to tell you in a little bit again, but it's a good question to ask, can I see that what I get is actually the Ayyer 2 and the Ayyer 1 process from this strange formula? I'm going to show you, and the answer is yes, it's very easy. I don't even have to check, I don't even have to use this connection with the older results. It's really completely apparent. So it's even this operator here that's containing the old Ayyer 1 and Ayyer 2 kernels. So that's the first one. The second remark that I wanted to make is that this can be done for other models, not only for TASEP, let's say for other similar models. It can be done for anything, but it can be done for, it cannot be done for anything, but it can be done for any model which shares some structure, which is what we're going to use. So, for instance, one has last passage percolation. That's a little bit of a cheat because it's the same model as Leandro was discussing yesterday. So that's with exponential weights. One can also do last passage percolation with geometric weights. So instead of putting exponential random variables, one puts geometric random variables. And this is the same as a certain version of TASEP in discrete time. One can also do something called PNG. And one can also do something called Pouchet-SEP. So this is just for those of you who know what these things are. And it can be done for other things as well, but this one is interesting as well. This is Brownian TASEP or Brownian last passage percolation. It can also be done. So at least we have like a family of models that are going to this fixed point. It cannot be done for many other models for which, okay, we believe it should, the conjecture is any model in the class should go to this, but you need some very special structure. So for instance, if you do the asymmetric exclusion process, instead of the totally asymmetric exclusion process where particles can jump to the right and to the left, this structure is broken. And if you want to do something like the KPZ equation, then for now there's no hope, as far as I know. Okay, I want to say maybe one more thing. Yeah, proving the theorem rigorously that there's convergence to this, that seems to be, for now, well, I shouldn't say no hope, but we don't have the tools yet. But okay, if you use if you use the replica method, I believe now, okay, so there were attempts using replicas to do this before, and it's not clear if the answer that was obtained is the same as this. But I believe that if that was the case, it was just, so this is a paper we had from some time ago, and it follows from some work of Herbert of trying to do something like this to try to get the Ayyer-2 process. And it's not yet clear if the two things are the same. That's actually an open question up to a point, but I guess one could sort of try to do it by replicas and get it. I mean, that's actually a natural problem from the physics side. Okay. Oh, it was you. Sorry.
So it's possible to make simulations and try to validate the for the KPZ.
So I think for the KPZ. So it's there's yeah. So physicists do some simulations. I really don't think anyone doubts this conjecture. So it's been always clear that you have convergence to the Ayyer-2 process, Ayyer-1 process, and it was also clear that there should be convergence to something. Which is going to depend on the initial condition if you have a more general initial condition. And the strong KPZ universality conjecture, which is really behind all this work, is, I mean, all this belief, I should say, it tells you that it should be a unique thing, and we computed it for one, so it should be the same for others. I mean, what you would have to do is maybe choose some other strange initial condition and check. But it's also not, I mean, the problem is that the numerical computation of what you get here gets a little bit more complicated in more complicated cases. You could do it in some specific cases. But for Ayyer-1 and Ayyer-2, you can get nice, because, I mean, if you want to validate the conjecture, what you have to do is really compute this numerically. It can be done, but you're going to see that this kernel gets a bit more complicated. Okay, so the last comment I wanted to make is that in the theorem, the initial condition can be random but independent of everything else. I mean, from the evolution of TASEP. There's no problem. So we can take random initial conditions and take the limit. The formula, this formula, I should put it here, such that H0, I can really take H0 can be random, but the formula is only done for deterministic H0. If you want a formula for generally, for random H0, then, well, you just have this formula and then take an expectation next to the independence. So the theorem is true for random initial conditions, and you get convergence to this Markov process with a random initial condition. The formula is really useful mostly for deterministic initial conditions. Okay. Do I really have 30 minutes left? I have 40. Okay. I have to sort of plan the rest of the talk on my head. Okay. Any questions? Because now I'm going to tell you who's this. I mean, the convergence, it's going in the end to depend on how we show convergence of the TASEP formulas to a formula like this with some specific operator here. And this operator will turn out to be interesting, and it's going to allow us to do several things. Actually, before telling you about the operator, I think it's better, I'm going to, so as I was saying, this operator is nice in several ways. It's a bit complicated, but it's nice. But actually, it allows us to prove several things about this fixed point. Before telling you what's the operator, I want to tell you the properties, because I told you it's a Markov process, but actually it satisfies many other things. And the things I'm going to tell you about will be proved either by using properties of the formula, either by using the exact formula, or by using properties of TASEP, or maybe both. Okay? So I'm going to tell you these properties because it's part of what makes this object interesting, but I am mostly not going to prove any of these properties unless I have some time at the end of the last lecture. So The first one, maybe this is not very important, but this is actually a failure Markov process. Don't know what that is, don't worry. But it can be proved that it's failure. Second one, it's 1, 2, 3 scaling invariant, as I showed yesterday. So I'm going to write it like this. Maybe I'm going to write it a little bit different than last time. So alpha minus t, alpha minus 2, and I put here the initial condition. There's an x here. If I do that, then what I get back is the same process with a scaled initial condition. Okay? So starting with H0, running the process and then scaling is the same as having scaled the initial condition and then running. So that's another one. So it satisfies many symmetries. As one would expect. So for instance, there's shift invariance. So if I compute HT x plus u with some initial condition, then that's the same thing as shifting the initial condition. And there's also, so this is shift invariance. There's also reflection invariance. And there's also some affine invariance. And you can look them up in the notes if you want, but affine, so reflection invariance means that if I compute h of t comma minus x, that's the same thing as h of t comma x with the reflected initial condition, which sort of makes sense. So if I take the initial condition and I flip it and I run it, what I get is the same thing flipped. At least, if you want, this all comes from the same properties for the height function of Taysep. And the affine invariance means that if I start with some initial condition and I take the initial condition and I add some linear function, then what I get is the same thing shifted by some other linear function. Okay, so that's all in the notes. So this is interesting. Brownian motion is invariant, and I think Leandro talked about that yesterday. Modulo a height shift. So what this means is that if you start with a Brownian motion, so Brownian motion is an upper semi-continuous function, so I can start my process with a Brownian motion, and I let it run, I'm going to have something that's always going to look like a Brownian motion, except that say I start with a Brownian motion that's 0 at 0, so it's at the origin and then it's two-sided. And then I run it, the position at the origin is going to be moving around. But if I take my process at time t, and then I recenter it at 0, then I see the same Brownian motion. And this height is the by-grains distribution that that Patrick was talking about yesterday at some point. It's coupled with the Brownian motion, but if you just look at the spatial evolution, it's a Brownian motion. Another one is that HTX is locally Brownian. This was also discussed by Leandro and I think a little bit by Patrick. So I'm not, again, it means that if you scale if you scale diffusively, what you see is a Brownian motion. The next one, okay, so HTX is locally Brownian. And also, so the fact that HTX is locally Brownian should tell you, and also the fact that Brownian motion is invariant, should tell you that you should expect the curves for fixed time to have the same regularity as Brownian motion. And that turns out to be true. So for every fixed positive t, the function, the spatial mapping, so x goes to h of t comma x, is Holder 1/2 minus. Okay, so it's holder alpha for every alpha less than a half. So for instance, this is proved using, this comes from taking the limit. So it essentially comes from TASEP if you want. This can be proved either from the formula or from TASEP, because this is also true from TASEP. This comes from TASEP because, as I told you yesterday, TASEP has a product measure as an invariant measure. So if you look at the height function, that's a random walk. And then if I scale the random walk in this 1, 2, 3 scaling, well, the 3 is not going to be there because it's only space, so it's diffusive, and I get a Brownian motion. So that's where these Brownian motion invariance comes from. But both this and this come from the formula. So I mean, it looks, you can't prove something like this just from TASEP. So you have to use the formula to show this, but it can be done. And you get this holder 1/2 minus regularity. Now the next thing you can do is to wonder, well, if I have holder 1/2 invariance in space, and I have this 1, 2, 3 scaling invariance, if you think about it for a bit, it looks like you should be able to transfer the regularity in space to regularity in time, somehow. And actually, if you make the computation, the guess, which turns out to be correct, and it can be proved, is that if I now fix the spatial variable, I have to be a bit more careful because this can only be proved up to only for positive times, but this mapping is holder, well, from the 1, 2, 3 scaling, one can check that it should be holder 1/3. So this evolution is holder 1/2 in space and holder 1/3 minus in time. So I won't prove these things. This one takes quite a bit of effort. This one actually comes from the variational formula that Leandro discussed yesterday and also Patrick, and this 1, 2, 3 scaling. But this will turn out to be very important. So I'm going to stop. I won't prove it, but I will say something about it a bit later. Okay, so what else do we have? We have ergodicity. This is Leandro's talk, which means that no matter what's the initial condition, as t goes to infinity, this goes to a Brownian motion, with some conditions on the initial condition in this case. Okay, I don't want to keep writing all of this. So we have a variational formula in terms of something called the Ayyer sheet. This is also what Leandro discussed yesterday, and it's also explained in notes, but I won't use it, so I won't get into the details. And is there one more that I want to say? Yeah, so for people coming from random matrices, this may be interesting. So you get information about the tails. You can show the following, and this comes from the formulas, that if I want to know what's the probability that h of t comma x is less than a, then I should say larger than a, then this has a decay. It's sort of the speed somehow, not the constants necessarily, look like the ones for the GOE or GOE random variables. So it looks like this. It's minus 4/3 a to the 3/2. This is on the right, divided by root t, and then plus a little error. And if you want to know what happens as a goes to minus infinity, then this is, the way to write it is this is 1 minus, it's larger than 1 minus, and here you get 1/12 a cubed divided by t, and again, plus some little error. Well, this is not for the case, of course. So, yeah, I haven't checked that. It's a good question. These are essentially sharp, so they have to fit. If you, for instance, if you set t equals 1, and you can see the narrow wedge initial condition. This is exactly, so this is gone, and you get, so it's exactly the decay of the GUE. Yeah, but I think, so this is also sharp in that sense. So it's sharp in the sense, okay, it's not sharp for any initial condition. So this one is not sharp for the narrow wedge initial condition, but it is sharp for the flat initial condition. So here you get the left decay of the GOE. So it's the most general one we can write in this generality. No, here is going to infinity. So here think of A going to infinity, so this is getting small. And here, yeah, so I should have said that. So this is A going to infinity, and this one is A going to minus infinity. Okay, so that's about the tails. But okay, it's not like the story for the KPZ equation where you don't have. So really, since you asked, Herbert, so this one, it's the usual argument. One just uses the Fredholm determinant, and this one is done just by comparison with the flat case. That's where it comes from. So because usually when you have a Fredholm determinant, it's easy to get upper tails. The lower tails are much harder, but here we can use comparison with the flat case. Okay. So let me, I just want to stop for a moment to explain in words how one proves the Markov property. Because this is something that has an effect in the actual paper. There's a long part which is devoted to estimates, and they really come, in a sense, they come from having to prove the Markov process, the Markov property. So the Markov property is proved as follows. So you start with, I think I mentioned this yesterday, you start with T-sep. You take this height function of T-sep, and that's Markovian. So at least the object you start with is Markovian, and then you would like to show that this Markov property is preserved in the limit. So you're computing the limit of a Markov process, you would like it to be Markov. That's not necessarily true. You need a little bit more. You need some tightness to actually show the Markov property of the limiting process. And the way to get tightness, well, so you have to get, again, you have to get tightness, so you have to understand some compact set somewhere. And the way to do it is to use regularity. Because if you look at the set of functions, of UC functions, which have bounded Holder norm on some given window, that's a compact set in UC. So that gives you, if you can control those sets, then you get the necessary tightness. The problem, so showing that this is Holder 1/2 minus is not so difficult. Actually, we have done it already earlier for the Ayyer 1 and the Ayyer 2 processes. But if you want to use this to get tightness, you have to show not only that this is Holder 1/2, you really have to show that all the approximating functions, so the approximating process, the 1 to 3 scale T-sep height function, that has to be Holder 1/2 uniformly in epsilon, locally. You need to be able to show that the Holder norm is well controlled uniformly in epsilon for a given initial condition. And that takes some effort. But after you do that, you have the necessary tightness, you have the Markov property of the approximating functions, and that gives you the Markov property. Okay, now I do have the time. I'm going more slowly than I thought, but so this is sort of the main point to understand what's the interest in the object. Now, as I said, I haven't told you who this is. I'm going to tell you who this is. Okay? And to introduce that, I have to introduce something we call the Brownian scattering operator, or the Brownian scattering transform. And then I'm going to tell you how from this Brownian scattering transform very easily you can define this fixed point kernel. So, okay, so I'm going to introduce some notation first. I'm going to, so let's say, given given an upper semi-continuous function, so I'm going to define an operator. It's going to be I'm going to write it now, but it's going to be the probability that a Brownian motion hits the hypograph of this function on this integral. Okay, so it's going to be an integral operator, and it's going to be, as I said, the probability that a Brownian motion started at U1 hits the hypograph of H. So if this is H, that's the hypograph of H, everything that's below H. Inside the interval, and okay, I guess I'm really defining, this is going to be the density of a measure. Okay, so I'm going to look at a Brownian motion, and I'm going to ask it to hit the region below the function and to exit the interval at U2. Okay, so it's a simple, it's just a Brownian hitting probability. Okay, so the picture is this. I have H, I have my Brownian motion, it starts at U1, it ends at U2, and I'm asking for the probability of an event like that. Okay, that it ever hits the hypograph of the function. Of course, you could start below the function, in which case, well, you hit it, right? So that's simple, but if you start above, then there's something to be done. Okay, so that's the first ingredient I need. So I want to make a comment. So we think of kernels of the form A, U, comma V, something like this. I will always think of those either as a kernel like that or as an integral operator itself, acting on functions on L2. So as an integral operator acting on L2. So what that means is that if I want to know what's A of f at a point U, that's the integral of A U V f of V. It's just the usual representation for an integral operator. Okay, so that's the first operator I want to consider. And next I need to consider another family of operators. So now I'm going to define something else. So I'm going to define St, x to be the following operator. E to the t-third derivative plus x second derivative. And I'm going to have to explain what this means. So here, d f is f prime. So different color. This thing here is just the Laplacian. Yesterday I was writing the little triangle or the delta for the Laplacian, but now I have third derivatives as well, so it's easier to write that. So if you set t equals 0, that's just a heat kernel, again. It's just a transition probability for a Brownian motion, a free Brownian motion. Okay, now you have this d cubed here, but nothing happens, so what this means, this means, if you wonder what, this is a sort of semigroup, and what that means is that if I apply STX to a function f, I apply at u, and if I compute the t derivative of this, then what you should get is 1/3 of the third derivative of STX f fu. That's what this thing is doing. And if you do dx of STX f of u, then you get, well, the second derivative of the same thing. Now, something may look very wrong here if you haven't seen something like this before, because I haven't said anything about x. So this is actually for all, okay, for all t comma x in R2 minus 0 cross minus infinity 0. So what does that mean? It means that I can take, so look, forget about this for a moment. X, in principle, it can be anything. So it could be negative. And that makes no sense. So the heat kernel is not invertible. Okay? But what I am saying is that as long as t is not 0, this makes sense for any x, even if I have this sort of backwards heat kernel. This is what I was mentioning yesterday when I said that you could actually multiply the Ayyer kernel by this backwards heat kernel. Okay, so why is that true? So that's true because you can write a formula, and you can check that the formula works. That's one way to say it. It's not only true because of that, but that's an easy way to say it. So looks bad for x negative, but it's okay. In fact, I can write a formula for the, so this is an operator acting in L2, and I can write a formula like this. I can write a formula for the integral kernel. Okay, and the formula is the following. It's as follows. Actually, what you do is you just go to Fourier space and try to do it there, and it just works. So I'm going to write it like this. So it's a function that's given as a contour integral, and it's tw cubed over 3 plus xw squared plus u minus v w. It's just that. If you do that, so exercise if you want, check that that function satisfies this. But it's pretty straightforward to see. There's a what? I can't hear you, sorry. Yeah. An I? No, so I should put that. So I'm on IR. Yeah. So usually you would write this with the usual Ayyer contour. You can do it like that as well. I just wrote it like this because it's clear that it's sort of, it comes from a Fourier representation. Yeah, if you don't see it, do the exercise, but it's pretty clear. You differentiate with respect to t, you get w cubed here, which is the same as differentiating 3 times with respect to u. It's really that simple. Okay, and then this thing, that's the kernel of the operator. This is for all t positive. For t negative, you have something very similar. I'm going to write it. But actually, you will, again, if you have seen these things before, you'll see that there's an Ayyer function here. And actually, the formula is the following. This equals minus t to the minus a third e to the 2x cubed over t squared. And now I'm going to get it wrong. So we won't use this, but I just wanted to write it because it's completely explicit. Plus u minus v x over t times the Ayyer function of minus t to the minus a third u minus v plus t to the minus 4/3 x squared. That's what it is. This is the same Ayyer function that I introduced yesterday, and this is very easy to get if you know what's the contour integral representation for the Ayyer function. This won't be too important for us. Okay, and for t negative, you can check that STX is the same as S minus TX adjoint, or transpose if you want. So you just take U and V and you flip them. Okay? So, okay, this is nice, can be done. And actually, STX satisfies the following. So I said this is, if you look at this formula, it looks like a semigroup, or as a sort of semigroup, and it's not only a semigroup, it's almost a group of operators. So the following thing holds if I compose STX and SY, let me call it maybe RY, then this equals ST plus R X plus Y. Well, whenever it makes sense, because I told you it has to be in that domain. So things go wrong if T or R and if T is 0 and this is negative. So whenever all the parameters, all the operators make sense. Okay? So this sort of object had already appeared in hiding, or not even so much in hiding, in earlier works. In particular, when one derives the Ayyer process, one sees exactly this sort of thing. Now I'm going to define this Brownian scattering operator, and I won't get to do much more today. So, definition. The Brownian scattering operator, or transform, let's say, of H in UC is the following object. So it is, I'm going to write it like this. I'm going to write the hypo here. So that's the name I'm giving it. It actually depends on a parameter t, or t positive. It is the limit as L goes to infinity. So I'm going to do again that heat operator that I was talking about before. I have to do something else. So first of all, I take this Brownian heating probability on this interval minus LL, and then I sort of conjugate by these S operators. So I put ST minus L here, and I put ST minus L adjoint on the other side. So that's the Brownian scattering transform. And of course, the question is, why does the limit make sense? I mean, why would something like this be well defined? Notice that if I take this out, I'm computing the limit of the probability of a Brownian motion starting at minus L, doing something and exiting at L, and then taking L to infinity. That does not converge, of course, or to anything meaningful. But this involves a Brownian motion going from minus L to L. So it's running for time L. Sorry, it's for time 2L. And here I am undoing, in a way, because I'm composing with the backwards heat kernel, I am undoing L units of time and here L units of time. And you can check, I had planned to do it, but I won't have time because I want to at least finish with something different. You can see it in the notes, and it's really not hard. So you can convince yourself that this limit makes sense, at least formally. It's really not hard. And if someone is interested, I can show you later. Okay? It's minus L on both sides. Yeah, because it's, so think of this. So really, the way to prove it is, yeah, essentially the way, let me say in one word what's the way, well, a couple of words, what's the way to prove it. Instead of computing this, you do the probability of no hit. And, okay, actually I will do it, because I think it's nice. So, the probability of hitting H is the same as 1 minus the probability of not hitting H. And actually, this is a transition probability for a Brownian motion. So what I should write is, I should say that this is the probability of hitting H is the probability of a Brownian motion going from U1 to U2 without any other restriction, minus the no hit probability, which is defined in exactly the same way, but now I ask not to hit. Right? Now, I can just look at the probability of no hit, because the probability, the one for the, let's do it like this. This is really, it can be written like this. This is the transition probability for the Brownian motion on a length of time of size 2L, minus the probability of not hitting. But this composed with that, gives me the identity because of this nice thing here. So this part is easy. So I only need to worry, about the no hit probability. Okay. Yeah, because the other one doesn't even depend on L. All the L's cancel. But so I'm going to give a sketch. So how do you, one way of writing this no hit probability is the following. I can say, okay, I have to go from time minus L to time L, and I have to go, here is H, I have to go from U1 to U2 without hitting the hypograph, so the function should be below. So here's the function. And I want to go from here to here without hitting. Well, that's the same thing as sort of picking a point on the middle and then sending a Brownian motion one way, asking it not to hit, and sending a Brownian motion the other way, asking it not to hit. So you can check that this, what I said is actually literally true. So this equals the integral from H at position 0 to infinity dz of the probability of no hit. So first I'm going to send a Brownian motion backwards. So it's going to be time 0 to L, but it's going to be no hit H minus. So here H minus of x is sort of H going in the opposite direction. So I'm going backwards. And I want to send it from Z to U1. And then times the probability of no hit H plus, say, so it's going the usual way, from Z to U2. Okay? So there's something easy to check here. I mean, why would the measure be Lebesgue? But this is just because it's just composition of essentially Brownian transition probabilities. So I can write this, but now I write this as follows. This equals the integral from, myself more space, the integral from H of 0 to infinity dz. So now I'm going to undo, so I started with the hit probability and I went to the no hit probability. Now it turns out to be convenient to go back to the hit probability. So, well, the no hit probability, again, that's the same as the probability for the transition of the Brownian motion minus the hit probability. So that's e to the L Laplacian z u1 minus the hit probability. But the hit probability, I can write it as follows, and it just turns out to be convenient. minus the integral from 0 to infinity ds, so s is going to be the heating time, the probability that the heating time of the backwards part of the function is in ds. Then, so I should maybe do a little picture here. Again, I need more space. So here is h. And what I'm doing is I'm starting somewhere above. I'm going to exit somewhere. But there's a point where I'll hit. This is tau equals s. And once I hit, the rest of the evolution of the Brownian motion is free. Right? Because the only thing is that I asked is that I have to hit. This Brownian transition probability with the no hit, with the hit condition can be written as, first I look when I hit, and then from that point on, so how much time do I have left? I have time L minus S left to go. I have to go from, well, wherever it is that I hit, and then I have to exit. Oh, here I should say this one starts at Z, and I should exit at U1. So this is just a way to rewrite this term. And then this is going to be multiplied by similar thing. Or H plus. Does that make sense? So I write the probability of not hitting on one side as 1 minus the probability of hitting, and the same thing on the other side. So I get these two guys. But now, look at what happens. So somehow in this whole thing, what I managed to do is I isolated these heat kernels. So there's an e to the L d squared. Here there's an e to the L minus S del squared. And they're all acting on the right variable somehow. So there's U1 here and U1, which are that's the variable coming from this side. So when I compose with this one, this minus L, what it does is that it cancels that. It exactly cancels that, and here you get the identity. And here, what you have is that this is canceled as well, but actually there's an ST here. So really, here what I get is ST of 0. Again, because of this composition, I have ST minus L, and here I have plus L. And here I have ST minus S, because of the L that canceled. So you see, from the formula, oh, and I'm sorry, I made a little mistake. So here this should go from 0 to L, right? Because the heating time was supposed to occur before L. I hit the final time of my lecture. But let me finish this. Actually, I want to finish with something very quick later. So now, when I apply that on the left, that's gone, and the only L is this one. That's the only L that's left. But if I take L to infinity, well, I'm going to get the integral from 0 to infinity, and that's it. Of course, I have to show that that convergence happens in the right sense, but that can be done. So this one goes away, and here I'm going to get exactly the same, and the ST comma minus L that's acting on the right, it's going to arrive to something very similar. So that's a way of seeing that this limit actually makes sense. But what's making this work is the fact that I have this ST here. Because you see here I have ST of minus S. If this was 0, this would be a backwards heat kernel and it would not make sense. But thanks to the fact that I have that third derivative, this is completely legal. Okay, so just to finish, I told you who is this Brownian scattering transform, and this was all to tell you who's this fixed point kernel. And the fixed point kernel, now it's very easy to write. So definition, the KPZ fixed point kernel is I guess from tomorrow I'm gonna stop writing the hypo. Okay, in terms of notation, the only new thing here is that I have an X. And that's simply because all I have to do is to conjugate by this heat kernel. And that's the answer. So what this is telling me, it's actually telling me something. Well, here there should not be an X. Yes. So you take this Brownian scattering operator and you sort of, this is the general operator, and if I wanna, so remember that what I'm supposed to be doing here is that the probability that this is less than A is the determinant of I minus this guy in L2 of A infinity. So somehow what this is telling me is that if you want to know what's the probability that this fixed point process stays below A, and the same thing would work if you have a multi-point distribution, then what you have to do is essentially compute the probability that a Brownian motion, well, in this case it has to hit the, it's not that it stays below, but it actually hits. There's a sort of inversion. But you can express the distribution of this fixed point process in terms of the heating times, essentially a heating problem for a Brownian motion. Instead of, there's a sort of projection to this Brownian motion. You do this, you build this weird operator, and then you somehow undo something, you compute this determinant, and out pops the right formula. So what I'm going to start by doing tomorrow, essentially what I want to do is show you that, and some of you may already see it if you start thinking about it, but it's very easy that in the area 2 and the area 1 cases, now I have an explicit formula. Here it is. If I want to show that the fixed point process at time 1 with the narrow wedge initial condition gives me area 2, what I have to do is I have to compute this heat probability, I have to compose with that, and I have to take a limit. But the narrow wedge initial condition is completely trivial if you want to do that. It's absolutely trivial. And the flat initial condition is not absolutely trivial, but almost trivial. So you get it straight away. So in particular, this kernel becomes the old kernels in those cases, but in general, you get a formula, and this formula is going to depend on some Brownian heating times, so they're hidden there, but you have a perfectly good expression. So tomorrow, I'm going to show you how to recover that, and then I'm going to show you some other things you can do with this formula. So you can sort of recover some sort of exact integrability in a sense of the fixed point just by using the formula. Okay, thanks.